All right. Thank you very much. Um, Again, I appreciate the name of the company that just came before us, the Non-Fictional Labs. Again, I feel like a lot of the things that we like to talk about are in fact science fiction labs, so it tends to be appropriate. So this is the title of the talk that I sent to the organizers at some point. A more accurate talk is probably just going to be weird nuclear magnetic resonance, ways that we have actually been trying to translate this exotic NMR kind of experiments into useful things. So talk about three main areas. One of them is a relatively old story, one is a relatively recent story, and then one is, at the moment, a little bit of science fiction. So we'll start with the story of some low field MRI. This is actually, this is largely from before my time, actually. This is work related to Ron Walsworth. I figured this since I think he was the originally invited speaker, we'll go and do a little bit of that. So back in the 1990s, while I was watching cartoons, Ron and his coworkers were working on the development of hyperpolarized helium-3 and xenon-129 nuclear spin masers for assorted fundamental physics experiments. For example, trying to look at limiting Lorentz violation as the Earth rotates around. So deep, weird science. What we eventually see is we have this atomic physics experiment in the 90s. Then in around the 2000s, we have walk-in MRI built up at Harvard. And then now that's actually been translated out into a commercial portable MRI system that is available in hospitals, also important for helping out people in the developing world. So a little bit earlier, when they're trying to do some early low field MRI, they figured, hey, we have this spin polarized helium, we have this spin polarized xenon. What if we build a little MRI to look at it? They took some pictures of some fancy glass blowing. Then the more natural thing is, let's make one that's actually big enough that we can look at lung imaging. This is, again, xenon lung imaging, as well as helium-3 lung imaging, is always kind of right there on the edge of full FDA approval. It's largely there. It's done in clinical cases. It's not common by any means, but it's definitely technology that exists out there. But so in order to make a low field MRI system, you have to make this kind of ridiculously big coil system. I've seen some of these old ones. I've seen the more recent builds, and it's just this huge electrically shielded room that's just made out of copper mesh with these really huge water-cooled magnets inside of them. It's peak crazy physics building. So then Matt Rosen, who actually I think was probably doing a lot of the glass blowing with Ron in those previous images, built an even nicer one of these magnets over at Martinos next to Mass General Hospital. So the 2010s showed that you can actually get usable brain MRI at extremely low fields. This is, I think, 6.5 millitesla. So it's a lot bigger than the nearest field, but not a big field by any means. And then two of them, along with Jonathan Rothberg, decided, hey, this actually works. Let's form a company. They called it Hyperfine because they're physics nerds. And the product ended up being called Swoop. It is a portable low field human MRI. It's FDA approved. It uses permanent magnets to establish that field. So it is also relatively low swap, especially for an MRI. Doesn't require helium, also convenient. And it's been shown in all kinds of press-related kind of scientific efforts. You can see, you can look at if you have COVID patients in the ICU, you can bring your imaging system over. You can take a look at what their brain is doing. In some of these more extreme cases of COVID response, we had no idea what was going on. So if you can actually see what the patient's brain is doing while they're in the ICU, that's tremendously helpful. And these images are even better looking than the ones we had before. Turns out that Matt Rosen was one of the sort of early adopters of machine learning and AI. And now he gets to go to a whole lot of conferences and receive awards for being at that forefront of showing that you can actually use MRI. You can actually use AI for MRI imagery construction, make things look better, deal with the fact that at lower field, you have less signal, you have a lot of other things that are limiting you. But if you use the right tools, you can actually get a lot of that back and get up with nice images. So yeah, as of 2025, if you take a look at how these images look, as AI gets better and better, images get better and better, and these things just keep on working. I think the Gates Foundation, bought a whole bunch of these so they can go deliver it into sub-Saharan Africa. This is allowing, because again, a normal MRI instrument, while they're very common at US hospitals, in a lot of the world, this is just totally unavailable. And it's really an essential technology, not just for looking at your brain, but if you have a wide range of other issues, oftentimes MRI is the best tool to look at that. It's if you don't have, and X-rays are also maybe portable, but MRI is really a good example of something that can be brought to everybody with the right system. So with that being done, a couple of years before I joined in Maryland, Ron was poached from Harvard to come be the director of the new Quantum Technology Center at UMD. You can see a whole lot of Maryland-colored advertisements about how we're going to have partnerships and intellectual property, and we're going to bring societal impact with near-term applications, which that is our job. It's probably all of our job to some extent. These are all kind of the usual goals. So if you go on the website, you can see all kinds of other exciting looking things about how we're going to innovate with transformative quantum technology, translate quantum societal impact, and educate the next gen of quantum leaders, which is a fancy way of saying that, we're going to do science and we're going to train students how to do it, which is also nice. And basically our goal as compared to, University of Maryland has, it's like 250 faculty working in quantum science. They've kind of a ridiculous wealth of people. So we have so many different institutes that we have to have different missions. The Joint Quantum Institute is working more on the fundamental side with NIST. With the Quantum Technology Center, our mission is really translation. It's finding a way to take technology that is about ready to work and prove that it can actually be useful, so we can then hand that off to a company who can go develop the product and make it into a real device. So now I'm going to tell a little bit more about the story that I've been a part of, which is what we call entanglement enhanced MRI. Again, this also began in a weird way and has recently turned into an actual product. So in terms of my personal origin story, I guess it's, when I was an undergrad, actually I was working in an NMR lab that was looking at spider silk. And I was actually bitten by an isotopically labeled spider. This is a true story. They had to go feed them amino acids to see what would happen to them. You get much better spectra, so you can actually look at distances and understand how the protein structure works. Unfortunately, it was stable isotopes, so I didn't get any superpowers that are of any use, but I got more interested in sort of weird nuclear spin behavior. So then, famously, when I went to grad school, just a little ways up north in the Bay, my advisor at, famously in the 80s, when a student had, accidentally quenched a NMR magnet, said, all right, you know what? Your new project, zero field NMR. Then it turns out you can actually do it. But if you think about how normal NMR works, if you have nuclei with unpaired nucleons inside of them, proton or neutrons, they have a magnetic moment. They have spin and therefore a magnetic moment. If you put that magnetic moment into a magnetic field, you see a difference in the actual precession frequency of this magnetic moment. And if you look at spins in a molecule, as you have slightly different magnetic fields at slightly different locations, you get different resonances. You can think of this also as just having a sort of local, atomic scale susceptibility inside of your molecule. So different places in your molecule have different electron density. This gives rise to a very slightly different magnetic resonance frequency. And because these spins couple so outrageously weakly to everything, unfortunately, including your detector, but also to the environment, you get these really exquisitely narrow lines and you get incredible chemical resolution. So we end up with this, what we call the chemical shift, which again, physicists thought was this absolute nuisance in their nuclear physics experiment. Again, then somebody in the chemistry department said, hey, this nuisance that you have might be kind of useful. So when you have noise and things, it's also useful to remember that the problem that you're having might actually end up being the strength of your technique. There's also some spin-spin couplings in there that tell you about other information. But this is sort of the routine, normal version of the science, which is great. You have that chemical specificity. You have the ability to measure things that are opaque. You can measure much, much smaller than the wavelength. Technically, all NMR is incredibly, or all MRI is incredibly super resolution. Given that at 300 megahertz, that's in a 7 Tesla MRI, your wavelength is a meter for that RF frequency. So everything is inside of that. Everything is Fourier-based imaging. It's non-invasive, it's not destructive. As long as you are not yourself made of magnetic material or overly magnetic ferromagnetic material, you'll be pretty safe. The problem is it's expensive. Usually it relies on these cryogenic magnets. We have a helium crisis that costs a lot of money. Sensitivity is really just terrible compared to every other analytical technique. You look at mass spec, they can measure down to a single molecule. NMR can measure down to hundreds of microliters. If you have any metal or conductive materials, you have a big problem because that RF penetration gets pretty bad. And if you have heterogeneous samples, everything goes to hell because that local magnetic susceptibility that is your chemical shift transforms exactly the same way as bulk susceptibility. So as soon as you have real materials, it's things that are liquid that can go into a nice glass NMR tube, those are great. You get nice, beautiful spectra. Most things in the world are not nice, clean liquids that can go into a glass tube. Most of the time, it's something messy. And that means that you actually can't use these techniques quite nearly as well because you end up with this big blob. So, notice that all of those problems on that side are kind of magnet related. If you have susceptibility problems, that's just because you have a big magnet. So again, it's chi times b. If you get rid of that magnetic susceptibility, or if you get rid of that magnet, then suddenly who cares what your susceptibility is because you're multiplying it by 0. So one can then ask, why do we have magnets for this nuclear magnetic resonance? One of them is chemical shift resolution. If you want to be able to see things nicely, you need to have a big field to have this chemical shift lead to measurable frequency differences. Also, the equilibrium spin polarization. Nuclear spin couplings to magnetic fields are incredibly weak. The energy difference between your nuclear spin sublevels is a tiny fraction of kT. So what you're looking at in a typical, relatively high field NMR measurement is 499,999 spins are canceling out 999,000 or whatever the number is, 500,000 versus another 500,000 canceling each other out. And that 1 or 2 spins per that total volume are actually giving you a signal. So the bigger the field, the bigger the signal, but again, it's still pretty small. And also, normal NMR uses a coil to measure that processing nuclear magnetization. You're measuring the time derivative of the flux. Therefore, the frequency of that magnetic field also is going to be, you'll be more sensitive to higher frequency signals. So again, if I'm talking about doing zero field NMR, the question is, do we actually need to do these things? The answer, spoiler alert, the answer will be no. You can use those spin-spin couplings instead of chemical shifts. They're incredibly sensitive to electronic structure as well. We're talking to quantum people here. Why would we ever do anything at thermal equilibrium? Let's get to a nicer, purer state. And instead of inductive detection, we can use non-inductive detection. For example, you can use an atomic magnetometer, like we were talking about before. These things are very good for measuring brain signals. They're very good for measuring heart signals. And they're actually pretty good at measuring magnetic resonance signals. So what advantage you really get, on the one hand, you have portability, you have wearability. You can imagine that you can actually have a combination of some of these tools like magnetocardiography. So you can have both chemical information and the direct magnetic information about what the heart is doing. Patients who have medical implants, you can still look at them. You don't have a problem of any artifacts being produced by metal in there. You have basically unlimited RF penetration. You can look inside of metal, and you'll be showed that you can actually look inside of a metal chemical reactor. While we have a heterogeneous reaction going on, there's no problem. You get nice narrow spectra. Everything goes right on through. And of course, there is no susceptibility problem at all. So that's all well and good. Again, that's you heard Ashok talking yesterday. He has also joined in on some of the fun of zero field NMR up at Berkeley, and he showed that you can actually start doing moving towards high throughput chemical analysis. One of the problems with normal NMR is that you can only put one sample in at a time, and this is actually a real bottleneck for a lot of pharmaceutical development. He showed that in principle, if you just have a whole bunch of these little optically pumped magnetometers, you can take advantage of separating your polarization of your spins. In their case, they found a 9.4 Tesla magnet that was sitting around in a mass spec lab. Then brought a magnetic field over next to it and showed that you can get a very homogeneous field at zero. Zero is easy to get. You just get a magnetic field and it's pretty much zero throughout. And you don't care about the homogeneity of your polarizing magnet. It's only there just to make the spins go in one direction versus the other. So in principle, you could measure hundreds of samples at the same time, which I think is a really cool thing. I saw this, I went to go and happened to be coming to a conference and got a chance to go look at that instrument. Very cool. Their field is at least 5 times bigger than any of the ones that we ever used for this kind of application. So they can really see things way faster and much more general measurements. So one way to do this is just to go to bigger magnetic fields and they can solve some of your problems. And this is absolutely true. However, that's the more general approach, but it's still not that good of a polarization. So we need a much purer state. We'd like to have a decent initialization fidelity if you want quantum jargon. And so what we use is actually some of the oldest quantum thinking that there is. If you think about dihydrogen, we know from the Pauli principle that since we have a bunch of fermions in this, the overall wave function needs to be anti-symmetric under exchange. So translation, electronic vibration in the ground state, these are all definitely symmetric. So then we know that the product of rotation and the nuclear spin state needs to overall be anti-symmetric. The ground rotational state of dihydrogen is symmetric. Therefore, the ground nuclear state has to be the spin singlet. So again, this is quantum 0.1. This is I was entertained by the fact that Heisenberg's Nobel Prize was for the creation of quantum mechanics and figuring out that we have ortho and parahydrogen. So this is the earliest quantum thing that there is, just about. So this is also a nice thing because it turns out that is a nuclear spin state that is a pure nuclear spin state. It is maximally entangled. It is a Bell state. In NMR, we don't get pure states. We dream of pure states because all that we have is basically just a whole bunch of garbage plus a tiny little bit of actual spin magnetization. Well, with hydrogen, you take it, you cool it down to 30 Kelvin. You can do that easily in a whatever the cheapest closed cycle cryostat there is. You add some rust for catalyst, basically. Then you can extract it and warm it back up. And as long as there's no additional paramagnetic stuff to relax it, it stays in that pure state for weeks. So you can actually literally have a bottle of pure nuclear spin state that you can walk around with. Actually, on all liquid hydrogen that is transported anywhere is actually transported as parahydrogen, because actually the separation in those rotational states is so big that if you accidentally quench it down, you can end up boiling off all of your hydrogen and blowing it up. So actually, just for safety's sake, all of the liquid hydrogen you ever encounter is actually all in exactly the same nuclear spin state. So it's just available around us. One notable thing is that nuclear spin state, the singlet, has zero magnetization. It is totally non-magnetic, totally unmeasurable by NMR. That might sound like a problem, but again, the trick is that you have to break that symmetry. As long as they are indistinguishable particles, you can't see anything. But if you do a little bit of chemistry, you can add that hydrogen pairwise across an unsaturated chemical bond, then you can actually break the symmetry. If you have 2 different groups on different sides, you see that singlet goes into only a pair of those states. And you get this huge, what they call a Pasadena effect. Parahydrogen and synthesis allowed dramatically enhanced nuclear alignment. This was shortly after Dan Weidekamp had moved to his job at Caltech. They actually also have an Altadena technique they came out with it later. So this is the other thing about NMR people. We like acronyms. Then you can also use any number of other pulse sequences, various kinds of quantum control to convert that entangled nuclear spin state into measurable magnetization. So where we come to me next, after I've been doing some of this zero field NMR work, I graduated, and our collaborator, Dima Budker, was moving to Germany to go be the director of the new Helmholtz Institute there, connected to the GSI accelerator facility. So officially, I had a postdoc fellowship that was for the purpose of designing a dark matter scattering target based on polarized nuclear spins. So for the cosmic axion spin precession experiment, potential dark matter candidate is the axion, and it can interact with nuclear spins, behaving like a fictitious magnetic field. Basically, you ask some theorists some questions, and you just build the world's most sensitive NMR experiment, and you attempt to look for dark matter. And for any of these things, you need to have the best possible detector with the lowest noise. You also need the biggest signal you can possibly get. So we need to be able to hyperpolarize those spins to a very high level. And we kind of technically did this a little bit. At some point, I was just getting so annoyed with the experiment planning taking so long, because I came from a physical chemistry background rather than a big project fundamental physics background. So the fact that we had to think about everything before we built it, and that we couldn't just figure it out along the way, I said, "Hey guys, watch this. I'm gonna go see. I'm gonna just go take an instrument that I've already built, and we're just gonna see if we can measure dark matter. We know we won't, but I bet we can set a new limit somewhere." We set a very small new limit relative to some other experiments, and showed that if we were to actually go and do the hyperpolarization experiment, we would end up, really surpassing astronomical limits. But what we were really doing, for what we were, focusing on, was how can we improve this parahydrogen-induced polarization approach? People have done it, and you get a little bit of something, but it usually wasn't. So you weren't getting 100% polarization. You weren't getting 10% polarization. You were getting it at relatively low concentrations. So it's kind of fun, but not really that useful overall. So we spent some time. We went and built some chemical reactors. We figured out ways that we can maximize every step of the process. And, we showed that we can get a pretty good polarization. So we were something in the 30 to 40% polarization at a reasonable concentration. And we found that we could actually make it clean. So as a result, this was something that we could actually inject into animals. Really the trick was just that we crashed out of solution using acid-base chemistry. It wasn't really that hard, but by doing everything together carefully, we got good numbers. And maybe that's kind of the message of how you do a lot of that step while in academia, of how to get to translation, is just start professionalizing things. It's yes, everything, it starts out built with duct tape and chewing gum, but then go to the machine shop and make things look a little bit better, and things that tend to actually work a lot better. So then we were looking with this fumarate molecule. It's used as a marker of cell necrosis. It can also be used for treatment response in tumors. It can also be used to look for vascular complications in hypoxia-mediated cell death, in nephropathy and diabetes, and also can be used to look at myocardial necrosis. So just like we were talking about at the beginning of this session, now you can imagine the combination of this plus normal MCG to see not just what is happening to that electrical signal, but also what is happening to those tissues. And so we did some work at the very beginning of the pandemic that we probably weren't supposed to be in lab for anymore, but we snuck in, and we ended up winning a prize for it. Thank you, Germany. And it turns out the Helmholtz Association liked the narrative of using fundamental physics to eventually contribute to medical imaging. After that, again, there was a pandemic, so then they cracked down and wouldn't let us in the labs at all. So I moved to another city in Germany, to work at a company called Envision Imaging Technologies GmbH. You see that capital N and the capital V. They were originally doing a lot of work exclusively with nitrogen vacancy centers in diamond. There was this dream that, like, hey, we have this optically initializable spin system. Can't we find a way that we can translate that initialized nuclear, electronic spin state into nuclear spin states? Like, can we use this as a general tool for hyperpolarizing everything? The answer is no. You cannot do that. They tried really hard. They hired everybody that could have done it. If it was possible to do, they would have figured it out. Maybe someday this can be done. Not now. So around this time, they called me up and saying, "Hey, we hear that you've been doing some stuff with parahydrogen. We hear that technology works. If one were to start a project doing parahydrogen research, who would you want to hire?" So I recommended a couple of my colleagues who were graduating, and they started up, shortly afterwards. Then I realized that everything was going to hell in the pandemic, and I wasn't allowed to work anymore in Mainz. So I called them and said, "Hey, also, if you're still hiring people, I'd also love to come join." So I went over. Again, it's by the time that I got there, they had already pivoted over to parahydrogen because, again, it's a technology that works. So November of 2020, we had the version 1, what we called the FIP Pol 1 for polarizing. Notable inclusions, there's always a little Ganesh on any of these instruments, at least originally. And then, about 6 months later, we had built it into something that looks a little bit nicer. There's still a few, bits of weird cables sitting around. And again, the trick is that once you actually work with engineers and synthetic chemists and programmers, again, they can do things professionally. Like physicists or physical chemists as well, we tend to believe that we can do everything because obviously we are the smartest people. No. The best thing is to have physicists do physics and have engineers do engineering and have software experts make software because they're a lot faster at it. Then if you actually have a team of real different backgrounds, you can actually move a lot faster. And then there's still a bunch of weird stuff that you have to go figure out with your physics mindset, so it's fine. But it just means that your software works from day one. It means that your engineering team can actually make something that can be produced cheaply and quickly. So I got sick of waiting for the engineers to go do the tube bending, so I just sat there and bruised myself a lot with a tube bender. We eventually just figured out that the best way to control, to increase our spin polarization was just to wrap coils around literally every piece of tubing that we had. And it worked. So we went and we made measurements in Munich so we can demonstrate that we had a real product, show that you can actually measure this metabolism. And it just works. So it's like we had a press team that came in and wanted to go take a video of us doing something sciencey. They were kind of disappointed that you just walked up, injected something in, pressed a button, waited for a minute and a half, pulled it out, and you were good. The funnier part of this is that I had not been aware that we were doing it that day, so I was wearing shorts. It appeared that I was just naked in lab for the press shoot. This is not, in fact, the CEO and CTO berating me for wearing shorts that day. That would come later. And of course, there's other molecules that are more interesting for things. For example, pyruvic acid is useful because if you're looking for cancer, there's this well-known Warburg effect where you have a different metabolic pathway. That's kind of almost the definition of cancerous tissues. So if you put in pyruvic acid into normal tissue, you get out CO2 and oxygen. All good. If you put it into cancerous tissue, you get lactic acid. So this has actually been done for a while that you can go inject hyperpolarized pyruvic acid into patients. And by looking at the ratio of lactate to pyruvate that is produced in those tissues, you can tell where a tumor is. You can also tell where this tumor is before you can see it in an anatomical image. And it also tells you about the nature of the tumor. You can, how aggressive is this tumor? So it gives you early detection. You can avoid unnecessary treatments. This was originally approved for prostate cancer, which naturally ages by producing tumors. And is therefore, leads to a lot of unnecessary treatments because you just want to be safe. Well, just cut it out. And it gives you MRI in color. It's handy. So that also works for pyruvate. You can do it in a company. You run into funny limits. If you start doing things well enough, you encounter new physics. Our samples were so highly polarized that the nuclear spin magnetization was preventing us from polarizing anymore. We did some measurements, again, at low field and showed that actually the applied field was smaller than the field produced by the sample. So this was leading to problems in experiments. Some other smart people came in and said, hey, well, we can just add something that's going to decouple this effect, and that allows us to, again, get right back up onto that nice line, get ridiculously high spin polarizations. And we want to use it to do some other stuff. This is the dream that's coming eventually. You need a magnetic microscope. You can do that with NVs. We need hyperpolarized metabolites. I just showed you about that. You need to find ways around other funny problems, and we are currently working on that. And I'll go and just skip through all of this stuff real quick. Hey, look, we have a microscope. It's very good. Session 1 is awesome. Spectral resolution, susceptibility is a nightmare for diamond. It's 20 parts per million, the diamagnetic susceptibility. That's going to cause problems. We'll see as we go to higher and higher fields how big those problems actually are, or if I'm just worried about it. We like to go back to J couplings. We showed actually that we can do metabolic stuff at zero field before. So we know that we can do it just with J couplings, so we'll be fine. And in summary, yeah, going from pure academic science, even truly fundamental physics kind of stuff, can go very nicely into real commercial products. Envision has since grown to be a incredibly large company. You can see the few people that were really a part of the R&D team when I was there, and now there's a huge number of additional support people also working on more research. And again, it's some of these pictures you can see, for example, James Eels there is now a group leader at the Forschungszentrum Jülich, which is equivalently a young professor. He also joined us in Mainz at some point, and also he was visiting in Berkeley in early 2020 when we were doing some work here. So I'd like to thank people that were involved in this, and then of course also the current team in Maryland that's working on developing this next new potential product. I think I've entirely used up my time, so thank you.
John, I appreciate it, especially the growing, heartbroken community of NV physicists trying to commercialize technology successfully. We will open for questions. We still have a little bit of time, and for lunch. Maybe I'll sneak then a quick one.
Yep.
You snuck past or skipped past the last part. Can you maybe just tell us more about how do you commercialize this final part?
Well, so the next step is going to be that we need to actually make it work. So it's there's a few challenges. We're able to measure NMR with similar devices like this. One thing is that I don't know a whole lot about microfluidics, so we're working with a lot of colleagues that we're kind of just going with as many collaborations as we can to see which one of them actually sticks. And a lot of it is just the same grinded out stuff that you have in normal precision measurement. It's that you just have to keep on going until it works. And we have ideas about what the applications are going to be. Sort of our thought is that okay, like if I have a pixel by pixel NMR camera, basically, this is probably going to be useful for stuff. I've imagined that okay, what if we take a tumor sample from a patient and we split that up into a whole bunch of different microfluidic wells. Maybe we can be flowing stuff through that, and so we can mimic the appropriate conditions. Then we throw in some of that hyperpolarized metabolites and see how that metabolism is going. And in addition to that, we can apply a different treatment to every one of these different cell masses. And by looking at how that metabolism is changing, maybe that can actually allow us to have more information about how we can help to treat the cancer in that patient. Maybe we start doing pharmaceutical development. A lot of that is lab on a chip kind of going anyway at this point. Now that would allow us to, instead of just develop a bunch of these microfluidic platforms and then have to wait forever until we can accumulate enough material for normal NMR, maybe now we just can measure 100 channels in parallel all at the same time, just right next to that diamond. I can come up with a bunch of other science fictional things, the trick is once we can actually develop the device, then we can imagine, finding those use cases and then proving that it's useful and valuable to a company.
Excellent. With that, I think we won't be delaying lunch anymore.
Right.
Peter, is there time for lunch?
I think so, yeah. And I assumed a lot.
All right.
All right.
Well, let's thank the speakers
Sure.
again.